The next subsection is about spectral clustering, and we will study this from a graph partitioning point of view. Clustering in general is a task of grouping a set of objects in such a way that the objects in the same group or cluster are much more similar to each other than those in other groups or clusters. Spectral clustering techniques in particular make use of a spectrum or a tangent values of the similarity matrix of the data to perform certain dimensionality reduction before clustering them into fewer dimensions. These methods are very attractive nowadays because they're very easy to implement and they're reasonably very fast, especially for sparse data sets up to several thousands. In this process, we will refer to a set of heuristic algorithms, all based on the overall idea of computing the first few singular vectors and then clustering in a low, in several cases simply one-dimensional subspace. After understanding the theoretical concepts behind spectral clustering and graph cut methods like ratio cuts and normalized cuts, let's move to the practical implementation of this problem. As the problem statement states, in this segment, the focus is on using spectral clustering as an approximation solution for a K-way graph partitioning problem. And we try to solve this graph partitioning problem for large-scale undirected social network graphs using two common spectral clustering techniques, ratio cuts and normalized cuts. Let's start with the algorithms used. We actually used two algorithms here, one for the unnormalized spectral clustering, another for the normalized spectral clustering. In the unnormalized spectral clustering, we employ ratio cut, whereas in normalized spectral clustering algorithm, we employ normalized cut. In the first algorithm, we take a weight matrix and cut the graph into k parts. Then we construct a diagonal matrix D, and then we compute the unnormalized Laplacian L, and using that we compute top k eigenvectors for the Laplacian L. Then from the matrix we find out the vectors as columns, and then in a loop we find out the vectors corresponding to the ith row of V. Finally, we return the clusters, and the same is employed in the normalized clustering algorithm but with slight variations. What we have here is that the normalized spectral clustering algorithm uses a different Laplacian matrix L and normalizes the eigenvectors before using k-means to cluster them into k partitions. But both the algorithms stated use the same framework and two different graph Laplacians. The main trick is to change the representation of the eigenvectors vi to point to yi belonging to r to the power k. This change of representation enhances the cluster properties in the data so that they can be trivially detected in the new representation. Moving forward, let's talk about the experimental implementation of it. The implementation of these algorithms is actually very straightforward. We use MATLAB for it. Before each algorithm, we first simply use a simple Python script to prepare the graph data into a matrix market format. In the unnormalized spectral clustering algorithm, the Laplacian matrix is symmetric. In the normalized spectral clustering algorithm, the Laplacian matrix is symmetric positive definite. Thus, we used MATLAB functions EIGS to compute the top k eigenvectors. During the k-means phase, we also apply MATLAB function k-means, but one issue during this implementation is that sometimes when we use EIGS function to compute eigenvectors, not all the eigenvectors converge. Also, because the results of the k-means is largely dependent on the initial condition, the solution of this algorithm is not deterministic, and in worst times, empty clusters will be formed. We actually use 4 different graphs for the experiments. The very first one is a block directional graph. The next one is an enroll email graph. The third one is an RCF collaboration graph, and the fourth one is a charity net graph. Let's see each of the matrix views of this graph independently. The first one is a generated block directional graph which contains 4 connected components, and it is to test the correctness of our implementation of the two algorithms. The second graph is an undirected graph, the enroll email graph, where each node denotes a person. One edge between two persons implies email communication between these two persons. The third graph is one category of R-zip collaboration graphs, each node of which is an author in an R-zip network, and there's an edge between the two co-authors. The last one is a bipartite charity net graph, which records how multiple donors donate to different charities. From the matrix view, we can see that both the test block directional graph and the charity net graph has different disconnected components, which makes clustering and partitioning much easier, while the other two graphs have either only a few connected components, like enroll email, or multiple uniformly distributed connected components, which makes clustering or partitioning a relatively difficult task. Moving forward, what are the results we got from the implementations and what do we observe from them? By employing ratio-cut algorithm for the graph partitioning, the first we saw the results of partitioning the test block directional graph. This graph has 4 connected components, and using k is equal to 4 to perform a ratio-cut algorithm, we successfully get optimal partitioning solution with 0 cuts. The following graph table shows the results of performing a ratio cut on enroll email graph and the RZIP collaboration graphs, where k sets as 6, 8, or 16. As you can see, for partition numbers of 6, 8, and 16, for RZIP collaboration and for enroll email collaboration graphs, we have varied partitions. This table shows a great reduction of the total cuts compared with the randomly picking edges as cuts in the graph. However, we can see from the table that the size of partitioning is ill-balanced for RZIP collaboration and enroll email graphs. The reason behind this is the topology of the graph. As we have stated that the enroll email graph contains only a few connected components, the RZIP collaboration graph contains multiple uniformly distributed connected components. This is much more visible in this two graphs that have been plotted from the experimental results. You can clearly see, as compared to ratio cuts where there is approximately 0 cuts can be obtained, random cuts have a much more variant observations. This figure shows the edges of cut and total edges in graph ratio for Enron email as well as for RZIP collaboration graphs using ratio cuts algorithms. This next experiment is done on a weighted bipartite graph of CharityNet, and as we have a very nice topology of the graph itself with 27 connected components, we get much better result in terms of the balance of partitioning when applied normalized-cut algorithms to it. As you can see from the figure, which is a size of 16 partitions when applied to n-cut algorithm on the CharityNet graph versus the average partition size, it is more or less near about to the average node size, even if not exactly equal. So we get a much better result in terms of partitioning when we apply normalized-cut algorithms on it. Moving forward, let's derive all the conclusions we got from the implementation of ratio-cut and n-cut algorithms practically. We can find out that both ratio cut and normalized cut can give a good approximation of the min-cut graph partitioning problem in terms of reducing the cut size. However, even normalized cut algorithm performed on weighted graph with multiple connected components still cannot give a very perfect result in terms of load balancing of partition size. Also, found out was that for dealing with X-scale graph data using clustering or community detection algorithms as a method, to do the graph partitioning is unnecessary for basic primitives such as breadth, first search, or the shortest path and the connected component labeling. Defining a good similarity graph and choosing the right Laplacian matrix is very important and has a great influence on the stability of the algorithms.